Okay, so in this tutorial we're going to pick up on our discussion on free fall, establish some important facts so that we can apply our kinematic equations to problems where an object is falling through the air. It may be falling up, it might be falling down, it might be doing both. The key thing to keep in mind is we know that when something's in free fall, it's continuously accelerating. We know the value of that acceleration. Now it's just an issue of applying it to our kinematic equations. So before we get into the mathematics, let's reestablish what it means to be in free fall, because not everything that's in the air is in free fall. That free part is important. Okay, so generally if you're free fall, you're definitely in the air. You could be moving up and moving down, but the only thing that's influencing you is gravity. Okay, something we'll talk about in much greater detail later in the year. You can't have anything supporting the object. It can't be wings flapping in the air. It can't be an engine or thrust from a rocket. It's simply under the influence of gravity. And so one of the most important things that would influence something that's in the air, that would take it out of free fall, is air resistance. And we talked about that and we demonstrated that yesterday or the day before. Okay, so our fundamental assumption about free fall is we're going to ignore air resistance. Okay, so if air resistance is ignored or has a small effect, and generally the effect is going to be small when we drop it over the distances of the ceiling or just out the window. If you drop it off a skyscraper, then we can't make that assumption anymore. But all objects, big or small, bowling ball, marble, we saw with a penny or feather, when there's no air resistance, they all accelerate at the same rate. And that rate, we know the value here on the surface of the Earth, okay? It's so important we give it its own name. It's called the acceleration due to gravity, okay? Not gravity itself, but an acceleration. It has its own symbol, little g, and it's right in the front of your reference tables. Little g equals negative for down 9.81 meters per second squared, okay? And that negative, again, indicates a direction. You are always accelerating down, even if you're moving up, or you're moving down, or if you're even moving forward, which we'll eventually see if there's no other influences. So a simple problem we can do is, well, how fast would you be going if you just fell? You slipped and fell, and you fell the height of basically from your behind to the ground. Okay, so we approach this like any other kinematic equation. I'm asking for how fast. So that's a final velocity because it's at the end of the fall. So we go through the process. So we know we're looking for that. So our initial speed, we do know, is 0. All right, so the initial speed is 0. And we can estimate the distance that we fall. Let's say it's roughly half my height or somebody's height. So let's say it's negative 1.0 meters. So at this point we might think, all right, I only have 2 pieces of information. Where do I go from here? Well, remember, we're falling, so we automatically know that the acceleration is negative 9.8 meters per second squared. Okay, so we can look for the correct kinematic equation that ties together distance and final velocity, and it's the Vf squared equals Vi squared plus 2AD. Okay, we can plug in the numbers. The initial speed is 0 plus 2 times negative 9.8 times negative 1. Okay, and that solves for Vf squared, so this whole thing is about negative 19 point, or actually positive 19.6, and then if we go do the square root of that, that's Vf squared. Okay, we will see that our answers are roughly negative 4.5, let's say, meters per second. The negative is important because we're moving down when we're falling. You won't get that when you take the square root. Well, you could if you want to, but just keep that in mind. Okay, so in more complicated problems, when we're moving up and down, we need some basic facts to help us out. So I've sketched here an object as it moves up through the air from time 0 to some time later on. We'll just call that t. And we can see a certain symmetry here. The object rises and it goes less and less distance with each interval. So here's the first interval, it covers a certain distance, the next interval covers less, then barely any at all. Then when it comes down, it covers the same distance as the one prior to that. And we can also look at speeds as well. Okay, we can see that if this were initially moving, let's say 40 meters per second, then after 1 second, it's going to lose roughly 10 meters per second. It goes 30, then 20, then 10. And again, I'm using 10 for 9.8 because they're close enough. Then at the top, 0. And then on the way down, -10, -20, -30, -40. So from that symmetry, we can establish some important facts. Okay, so I'm just going to erase all this because we don't have to have it. All right, fact number 1, we can see from here that the total time it takes to rise to the top is going to equal the total time it takes to come down. All right, so T up equals T down. And if you put it all together, we can say that's half the time in the air. And that's a really important thing to use in some of these problems. So when we go out and do a lab with air rockets, we fire it up in the air and we measure it to be in the air for 6 seconds. We can deduce that it was rising for 3 seconds and falling for 3 seconds. And that will help us solve other quantities about that flight. Secondly, we can see that at the very top, even though it stops for a minute, so we can say at the top, the velocity is 0. Okay? It's still accelerating there. That's a really important point. G is still -9.8. It's not 0, but it stops moving for an instant. And that's very, very useful in trying to solve problems because we know the final velocity at one given place. The last thing we know, and this is also important, is if we launch something with an initial velocity upwards, we already saw with the numbers, by the time it gets back to here, it's going to have the same speed, just in the opposite direction. So we can say that the initial launch speed equals the negative of the final speed when at the same height. Okay, so that symmetry can be useful. Alrighty, so we'll skip to, for right now, we'll come back and hit that later. Let's go to solve some problems. So I'll let you turn your paper over. We'll skip 3, we'll hit that later, and let's do practice problems. All right, so the simple one is an object falling a certain height. So in this case, we have a cat slips, falls a height of 2.5 meters, and we want to know how much time was it in the air. And then we can ask how fast is it going just before it hits the ground. It doesn't matter which order we do these in. We can do them in any order. The point is we want to use our problem-solving strategies to solve this. Okay, so we list what's asked for. So the first one, we're looking for time. All right, now we go with what are we given? Well, the obvious thing is the distance that it falls. All right, and actually it should be a displacement, so we want to put -2.5 meters because the downward part. Right, well, it doesn't look like we have much else, and we know we need 3 pieces of information. So what do? Well, we just go through the list and ask ourselves, do we know these? So do we know the initial speed? Yes, we do. We know that it slipped, so its initial speed was 0. Do we know the final speed? No, we have no idea. Nothing from there helps us out. The last thing we ask ourselves, do we know the rate at which it accelerates? Yes, we do. Since it's falling through the air under its own, or under the influence of gravity, we know that A is -9.8 meters per second squared. So now I can choose the right kinematic equation that ties together distance, time, and acceleration. And that equation, of course, is d equals VIT plus 1/2 AT squared. All right, let's plug in the numbers. So we can say -2.5 equals 0 plus 1/2 -9.8 times t squared. Okay, so we're solving for t. And do the math. I'll trust you can do that. We find that t squared is going to be equal to -5.0 divided by -9.8. That's good because we need to get a positive number. And if we take the square root of both sides, we'll see it's about 0.73 seconds. Okay? And so reflect on an answer. It's fallen 2.5 meters. It's in the air for less than a second. And from what we saw in class in our little exercise, that matches just right. So the next question, how fast we're going, VF. Well, we already have the same information, so this is pretty easy. There's a lot of equations we could choose. I'm going to choose the most straightforward one. It says our final velocity is equals our initial velocity plus the rate at which we accelerate multiplied by the time. So this just becomes 0 plus -9.8, right? We're still at the same acceleration. And now we know the time is 0.73 seconds. Okay, so that's pretty straightforward. So that's going to be approximately -7.2 meters per second. It's a negative meaning it's on its way down. Okay, so we want to be careful about the positive and negatives here. And notice again, it was just before it hits. It's not after it hits the ground and comes to a stop. So a common mistake students make is they say the final velocity is 0. No. The only time the velocity is 0 in a free fall problem is when it's at the peak of its trajectory. Okay, so we're going to use that fact for the next problem. So let's look at one more, and then I'll have you practice on your own. All right, so let's say a cat is tossed up in the air at a speed of 8.5 meters per second. Okay? In other words, it can't move up unless it's projected up. We can ask, how long will it be in the air? Okay, so let's go with our strategies. We're looking for a time in the air. Question mark. What do we know? Well, we're given the 8.5, which is an initial speed. It's upward, so it's positive. What else do I know? Well, we're not given anything else, but we go through the list. Do we know the height that it went to? Nope, nothing here. Do we know the final velocity? Ooh, actually we do. Okay, we can use our symmetry. The final speed just before it hits is equal to the negative of the initial speed. That's a handy little fact to know, so that I can say the final speed is negative 8.5 meters per second. That's only 2 pieces of information. What else do I have to think about? Oh yeah, acceleration. Do we know what rate of accelerating? Of course we do. Negative 9.8 meters per second squared. Okay, so what equation is going to help us solve for this? That's pretty straightforward. I can say that VF equals VI plus AT. So I'll put in the numbers. So I can say negative 8.5. You got to be careful of the signs here. Equals 8.5 plus negative 9.8 times t. So I'm going to subtract 8.5 from here, which gives me negative 16 equals negative 9.8 t, and then solve for it. T is approximately 1.7 seconds. Okay? So, to sum up, to do these problems, you're using the same kinematic equations. You know that acceleration is always negative 9.8. It's just that you have to use facts to sometimes deduce what the initial speed is, what the final speed is, or the speed at some time. Okay? So I want you to try B on your own, try C on your own. We'll do D together in class.